in 3-year project cycles. We finished the first track in 2000. We rebuilt in 03, 06, 09, 12, 15, 18, and then most recently cycle number 8 we built last summer, the 2021 track. And then since 2015, we've been in a formal partnership with the Minnesota Road Research Project. So we do the same work at the track that we do up here. There's been a growing focus amongst the track. You know, the track is a multi-state research cooperative, and there's a growing focus on safety with the state DOTs. And, you know, as we are working with, in some states, diminishing virgin aggregate resources and our desire to use reclaimed asphalt pavement that contains aggregates from other projects, there's a focus on hitting friction targets with mixes, and then hitting enhanced friction targets with some mixes. And that really is the focus of the content of this webinar that we're putting on today. But the basis of all this is the work that we're doing on the track, which has led to work that we're doing with states off the track. And I think maybe you might hear something about that as we go through the webinar this morning. So since 2000, we've literally done hundreds of mixes on the track, and we haul in materials from all over the country, from as far west as Oklahoma and Texas, and as far east as Virginia, and then as far north as Kentucky. So we've got a big footprint of impact, and a big footprint of raw materials, because we, you know, as I said, we haul in the virgin materials and the recycled materials, and we use binder grades that are appropriate for the various jurisdictions, for the DOTs and the private sector clients that are funding research at the track. We measure friction. I've actually got an error on the slide. Every month we measure wet ribbed friction on the track, and we've been measuring it monthly ever since 2000. So we have hundreds of mixes from all over the country. We have monthly wet rib friction data, and then we have quarterly dynamic friction tester data that we measure on the track. So it's a tremendous database of information that has great value as we do work with states to try to make roads safer. We actually did the first high friction surface treatment, which is, you know, HFSTs, in the 2003 research cycle. Well, that might actually make us some of the first HFST that was placed in the United States. And we did that in section E2 and E3. Some of y'all might be familiar with that. So our work with calcined bauxite on epoxy goes back a very long time. And we do 5 million easels, equivalent single axle loadings, a year on the track. And that's about 3 million heavy axle passes. So we've got a lot of abrasion data on the track. What we've seen with our HFSTs is they work extremely well on our facility with our trucks for about nine to 10 years, and that's an error too. 90 million easels, that's too much. 9 to 10 years, and I think 60 million easels. I'll get back into the data here in a little bit. I apologize. This is a rough week for us. But there's a point you're going to see in our data where the data just sort of falls off a table. And the reason why that happens is because as you gradually lose calcined bauxite over time, the material that's underneath it begins to dominate what's referred to as the tribology of the pavement tire interface. And in some cases, that's epoxy that dominates. In some cases, it's potentially lower friction materials underneath it. But the bauxite gets gradually scarce, more and more scarce, and you begin to lose those high friction properties. So because of this, FHWA on the track, through their participation and partnership with the state DOTs, FHWA said, well, we'd like to do some research to try to, number one, drive down the cost of HFSTs, looking at local friction chips. But then we also want to look at asphalt alternatives so that we can potentially avoid that drop off that occurs at the end of life for HFSTs, because that can be really hard for state DOTs to track that and kind of keep up with that from a maintenance and safety point of view. What we've seen in our data, then you're going to see here in just a minute before I hand off to Nathan, is that we've done something that we refer to as an enhanced friction thin lay, and we've done a microsurface that has bauxite blended into it And at the half-life of epoxy bauxite, all three of those are approximately equal, which means that it's potentially a really good asphalt-based alternative to the much more expensive epoxy bauxite. So we've gotten into the business, Nathan Moore, of designing aggregate blends to achieve enhanced friction performance. He's got a lot of really good experience with that. And then that kind of goes hand in hand with designing aggregate blends to achieve minimum friction performance. So the title of this implementation webinar is Enhanced Friction Mix Designs, but really just designing mixes for target frictions might be a better title for it. So I want to focus on that half-life thing that I was telling you about. This is data, and it's 30 million easels. That was the number I was groping around for in the haze of this morning here up in Minnesota building test sections. So 9 to 10 years and 30 million equivalent single axle loadings. The blue data that you see on this plot, those are the HFSTs that we placed in the 2003 research cycle. And as you can see, they do really well. They don't, they kind of drop off a little bit and then level off, and then they sort of fall off a table. They're just past about 30 million easels. And that's because now you've got enough of that underlying surface exposed, as you can see in this picture, that you've got friction being controlled by the underlying material, which can be epoxy or it can be that the mix that you covered up. But what we see here, and the blue data is from the 2003 track, and then the red data is actually from the latter part of the 2009 track, where we put down alternative chip test sections that were epoxy test sections with calcined bauxite as a control for FHWA. And it might be kind of hard to see in those pictures, but you see the exact same thing. When this is not like a delamination failure of the bauxite particles. This is just normal wear and tear of the bauxite particles, and over time they gradually turn loose. But what you see in those lighter colored plots that start out lower, but they all kind of intersect at about the half-life of the HFST. So at about 15 million equivalent single axle loadings, that thin lay that you see in that picture superimposed on that data graphic, it shows that everything kind of converges. So the thin lay that for us was 40% calcined bauxite, and the microsurface that was 50% calcined bauxite, at about the half-life of the HFSTs, they come together. So that's a really safe surface. It doesn't provide the outrageously high friction of the HFST early in the life, but again, out in the future, they come together, which means this is a really useful mix to put down, and you can do it at cost savings. So kind of the idea behind this research was, if you're paving a road and you can be running down the road with a conventional mix design, and if you get into an intersection or a curve, or a bad geometry where roads are coming together, and you're going to have some safety concerns, and you need good vehicle control or short stopping distance, you can transition from your conventional mix into a bauxite mix. So maybe substitute a material with the bauxite, and then when you pave out of that ugly curve or whatever it is you're trying to compensate for, you swap back to your normal mix design, so you can achieve enhanced friction performance without having to have an additional mobilization and the cost of epoxy and all that. So that was kind of the thinking behind the thin lay that was put on the track in that research cycle. So I'm going to hand off the control to Nathan, and he's going to take it from here.
All right, thank you, Buzz. So we're going to zoom out a little bit and maybe go back to pavement friction 101 to discuss some pavement surface friction basics. So when you talk about pavement friction, specifically asphalt pavement friction, you're really looking at two things: it's micro texture and macro texture. So the macro texture is kind of you can think about that as like what you can see with the naked eye. It's kind of it's it's definitely controlled by the larger particles of your aggregates in your mix. Aggregate microtexture, though, that's really controlled by the texture of those aggregate particles, and they both play a very important role in achieving a safe riding surface. So you can see as a vehicle passes over a typical pavement, it really requires both of these in order for it to be a safe environment. So macro texture, what that is doing is it provides a channel for water to run off without creating a film between the pavement and the tire. So that macro texture, you can just imagine it provides a channel. You're riding on top of those coarse aggregate particles, and the water's running underneath those tires in such a way that it doesn't create a film that would greatly reduce skid resistance. And we'll talk about that later. So that's really where macro texture comes into play, is it is critical to give the water somewhere to go so that you can reduce the risk of hydroplaning. Micro texture is important because over time, as your mixes begin to ravel out, and all that is left is some of your coarse aggregates. If that's what the riding surface is, you really need to make sure that those aggregate particles that are exposed, that are doing the heavy lifting, that they have good texture, that they're gritty, that they're rough enough to provide a good skid resistance. So those two things are both very important, although they play different roles in achieving good quality pavement friction. When it comes to pavement friction testing, there's multiple different devices to do this. Typically, you'll hear like the one on the left, what you're looking at, that's a lot wheel skid trailer. A lot of states use this to characterize their friction pavement network. And on the right, that's the scrim machine. Now, they both measure friction. They happen to do so in a different way, and the numbers are not the same. However, just from historical evidence, the data that you would get from the lock wheel skid trailer is about 3/4 of the data of the number that you would get from the scrim vehicle. So you may see like a number in the mid-30s, for example, with the lock wheel skid trailer. That would equal about the mid-40s on the scrim data. And this is useful information to be able to, even though they may be apples and oranges, you can at least kind of get on the same page when you begin to look at friction results. Now in the laboratory, we run the dynamic friction tester on, and we'll talk more about that here in a second. And I think Phil's got a lot to say about that as well, but you can also take that out in the field. But this also uses different units. So the dynamic friction tester, or we'll refer to that as the DFT, those numbers are in about the mid-0.3s, but you may measure the same pavement and you would get mid-0.3s for the DFT, about mid-30s for the lock wheel skid trailer, and about mid-40s for the scrim. But these are just helpful tools for us to be able to speak the same language depending on how different agencies or how different research groups are measuring pavement friction. Now, when it comes to pavement friction, you're not going to find a whole lot of information regarding like this is a safe friction number. It's different depending on different agencies and different locations. However, this ASTM's special technical publication from the 70s provides some very useful values for what most people would generally consider safe friction and unsafe friction, and they kind of break it up into 3 groups: good, I forget the middle, but acceptable and poor. So it's a really helpful resource that we've relied a lot on, and our numbers kind of at the test track line up pretty closely with what they viewed 40, 50 years ago with what a good what good friction numbers were. So what I'm showing you here, this is work from Sweden back in 2001. But looking at the crash rate reduction as you increase the coefficient of friction on your pavement surface. And so if you're down at a 0.25, you're not getting any crash rate reduction. That's kind of where we're starting at. But as you begin to move, in this case, we're looking specifically at high friction surface treatments, as you almost triple that coefficient of friction, going from a 0.25 up almost to a 0.75, you get a 68% crash rate reduction by putting a high friction surface treatment on a low friction pavement. And that's very important information. However, what I want us to focus on is let's look at, well, what can we achieve with our asphalt pavements? So even if you're down still close to that 0.25 to 0.45 range, somewhere in there, you can still see that even a marginal increase in the friction coefficient of your asphalt pavements provides a pretty substantial crash rate reduction. So then that begs the question, well, what can we do to try to hit certain friction targets in the laboratory in mix design so that we can make sure that the final roads that we're paving, that we know that in the future, whenever they do ravel and wear, that they will end up being a safe riding surface. And for anybody who kind of hadn't seen a high friction surface treatment up close, this is what Buzz was talking about earlier. The one on the left, that's that calcined bauxite. It's really great aggregate. It's very hard, very angular, and it provides an excellent riding surface on the left. But as Buzz mentioned, we've seen on the track where eventually those things can ravel out, and you may be just riding on that point on epoxy, which tends to be pretty slick. Also, in some of the work, and I'm hitting the high points here because Buzz has already referenced these two sections. When you put calcined bauxite in the actual mix, in this case, it was a 3/4 inch thin lay using 40% calcined bauxite. Well, even once you ravel out the surface, what's underneath it is just more calcined bauxite, and it's more good friction aggregate. And so that's a pretty critical finding that we found, that eventually, like Buzz mentioned, after about 15 million easels, these were performing as well as the half-life of the high friction surface treatments. So I'm going to go through and show you guys some of the stuff that we've learned on the track, how to design mixes for friction. This is still kind of a developing area, so by no means is this a answered question with done and dusted and settled. But I do think that we've found some pretty interesting findings over the years, and certainly in this past couple test tracks, we've got a really cool opportunity to look at how mixes go from laboratory testing to actual performance on our test track. So it's important, we need to incorporate terminal friction into mix design process. Now, some people want to think more about terminal friction being the very, what's the lowest friction that this is going to achieve in its lifetime. Some people may be more interested in the rate loss of friction from early life to late life. And these are all conversations that are absolutely worth having. The point is that we just need to have a criteria for these. This is what we are going to use as our metric for estimating good friction values. And what's really important is we need to investigate what affects macro texture and micro texture in the laboratory. So I like to think of this as a toolbox, so if you hand me a mix and you ask me to design a volumetric mix design or even a balanced mix design mix, I have a different set of toolboxes for different tasks. Well, so for friction, what tools can a mix designer use to meet friction targets in the laboratory? And then how do these affect the volumetrics or performance? Some of these questions remain unknown, and I don't think we need to get too concerned about implementing all of these all at one time. I think it's important for us to figure out, well, what kind of things can we change and tweak in the laboratory setting from an asphalt pavement to achieve higher friction. And then down the road, we'll figure out how those affect volumetrics. But we do have a little bit of performance with that. So I'm going to show you a couple of the tools that we've implemented on the test track, some of the work that we've done in the past couple cycles, and I'll show you some data from that. So one of the things is using what Mike Heitzman called the percent friction aggregate. And the friction aggregate, as he defined it in some of the work we did on the track in 2018, was the +4 material. So making sure that you are designing so that of the +4 fraction of your gradation, at least 50% of that needs to be of whatever good friction aggregate you have locally available or that you decide to use. And this lines up pretty well with some of the work that Becky McDaniel did, where I think that Becky McDaniel and Carol Kowalski have said about that you need 20% of your total blend to come from the good friction aggregate. And these numbers line up pretty well. It depends on if you're designing a coarse mix or a fine mix, but in general, the idea is you want to make sure that you've got enough friction aggregate, of good friction aggregate in your mix so it can do the heavy lifting. Now, an issue with this approach is this focuses heavily on macro texture. And as I mentioned earlier, macro texture is very important, but it's not the only story. And there's currently no really widely accepted method to predict microtexture of asphalt pavements. And another thing with this method, which I'm not saying it's bad, but it's just one tool that you can use. Well, what does this say about the effects on friction of your sands or your fine aggregate proportion? This method kind of ignores that. So you kind of have to think differently about those as well. And I'll show you some data that show really the effect of different sands and fine aggregates here in a little while. Now, when it comes to macro texture, though, macro texture is, you can get a pretty good estimate of what your macro texture will be just by adjusting the gradation. So what we're showing here is these are sections from the 2000, 2003, the 06, and the 09 track. So 4 different research cycles, all plotted on the same graph. Looking at the percent passing the number 8 sieve from our quality control extractions, really ranging from 10% all the way up to 70. And this is really interesting because this gives you an idea, and it certainly proves macro texture is affected by your gradation. So by aggregate selection and aggregate size selection, you can make sure that you are achieving good quality macro texture with your pavements. This is very important. In 2008, AASHTO published a document called Driving Down Lane Departure Crashes, where a water film of approximately 0.002 of an inch reduces tire pavement friction by 20 to 30%. Now, to give you a scale for what that is, that's about the average width of a human hair. This is really important, that if we can make sure that water has somewhere to go, we don't have to worry as much about our tire pavement friction being reduced by this amount. So macro texture is very important for reducing hydroplaning and things like that. Another example of using kind of this friction aggregate idea that I just talked about on the 2018 track comes here. So on the left, and I'm going to pop up a different image here on the right in a second, what I'm showing you is 6 or 7 different blends where we use differing amounts of a specific dolomite that it was prone to polish and produce very low skid resistance. So these are from the laboratory data. So we were able to kind of characterize the effect of different amounts of dolomite. Well, we did that in the lab, and then we paved a couple sections on our track. And what you can see is as you move from right to left, you're increasing the amount of higher quality aggregate. And so on the right side of that 50%, and we're talking that 50%, we're using the same friction aggregate definition that we discussed earlier. As you move from right to left, at least on the right side of that graph, you are increasing friction incrementally just by increasing the amount of higher quality aggregates that you're using. Now, one thing that is important is just because you're putting more and more friction aggregate in doesn't mean it's going to go up forever. Eventually, you have a ceiling, a threshold that those aggregates are going to hit. And from our research, and this is from an NCAT section that you can read out in the NCAT report listed on the screen. Eventually, that aggregate will kind of take over as the primary friction aggregate in that mix, and putting more and more of that aggregate in isn't really going to increase and isn't really going to affect the micro texture as much anymore. It's kind of taken over as the dominant aggregate in the blend. So this is one tool of really adjusting that percent friction aggregate to achieve certain targets. But then that also begs the question, well, how do you know, well, what's a good aggregate? Or what are the certain, how can I know these thresholds or these ceilings for my different aggregates if you have a couple of those at your exposure? And we'll get into that in a second. Another interesting thing you can do is if you've got multiple wrap stockpiles, you can actually measure 2 different wraps. And so I'm showing you here, these are 2 different wraps where I put together 100% wrap blends, mixed, I think 2.5% binder just to get the thing to stick together and hold and hold. And then I ran this through the 3-well polishing device and on our DFT, our dynamic friction tester in the lab. And it's pretty apparent these two wraps have two different friction performance and friction characteristics. This is an important finding because if you are really trying to achieve a higher friction, you may have millings from a certain part of your state that has better friction over there. And if you're trying to hit a friction target, you can use wrap selection even as a tool to try to increase your target friction. And I'm going to show you these color codes because it's going to show up in a few of the other slides. And what I'm showing you here, obviously, we don't want to say these are the friction numbers that are safe for everyone to use. But I think it's really valuable to put some kind of a scale on here so that folks, especially who are new to this, can say, well, how do I know? Is this good friction or bad friction? So what Buzz and I have started doing is we've started putting kind of these 3 zones on some of our presentations to give you, these are what we use at the track. So at our test track, which is not a publicly accessed facility, so we don't have to worry about all of the public safety issues that most mix designers and most agencies are having to deal with. These are just the numbers that we use at our track that overlay pretty well. And so you can see from some of these later slides that I'll show you, it just gives you a quick kind of index of what we're looking at and how we are assessing aggregate quality, at least on our test track. I talked about earlier about the effect of fine aggregate. This is a very small study that we did using that percent friction aggregate methodology as well. But I just wanted to put this in here to show fine aggregates, they can actually matter. So if you look at the blue dots, that's all with one, the same coarse aggregate. It's a good friction aggregate. But you can see there's 2 different kind of regions. You have one that's up on the top and one on the bottom. Same coarse aggregate. We swapped out fine aggregate sources, and that's the only change we made. We use the same wrap source and even the same proportions of friction aggregate, as you can see there from the x-axis. And yet we saw a noticeable dip whenever we switched fine aggregate sources. Not quite something we totally understand why that happened yet, but it was a pretty useful finding, if nothing else, to demonstrate fine aggregates should not be forgotten in the conversation about how to tweak mixes for friction. This is some work that we did, and I mentioned earlier about how can you figure out what those ceilings are? How can you figure out what your thresholds are if you're trying to get a good friction mix? Well, we took different aggregate types from a specific location. So this is not, I'm not talking about all quartzite or all granites or all sandstones, blah, blah, blah. But what we did is we made mixes where these were the dominant friction aggregates, and we even varied the proportions. So you can see low and high, or the L and the H. So we varied the proportions. We ran them through the 3-well polisher up to 150,000 cycles. We made sure we were well into, at that point, the friction lines had kind of flatlined, and so we knew we were at terminal friction. And we were able to, at least empirically, we don't necessarily know why, what aggregate mineralogy is driving this or things like that, but at least empirically, we have a way to rank our aggregates at our disposal. And so if we need a really high friction mix design, well, now we know, okay, well, we only have a couple options here. And this is another useful tool that, again, I think as this field continues to develop, we'll understand a lot more about what affects pavement microtexture. I think it's got everything to do with the aggregate, but even then, we're just not quite there. But this is a way that we can at least say, we may not know why, but we at least know that we can do this. We can at least know that we can characterize, if only maybe just on an index scale or a ranking scale, of which aggregates may be more suitable for specific jobs for that may require higher friction. And I'm going to conclude with a couple more slides here, just showing some examples from our 2021 track. We had two different mixes, and if I had more time, I could really get into the details about the mix design process. But where we did the previous slide, we did that same procedure. We looked at different aggregate sources. We identified which aggregate sources seem to produce the highest number on the DFT, which is a good indicator of pavement microtexture. We put those together. We put them on our test track. And now here we are almost 2 million easels in. And in the laboratory, these things were, we designed one for kind of a medium or a acceptable friction. And then we wanted to say, well, can we do this for a higher friction? And so far, so good. You can see the two sections are really kind of distinguishing themselves as different from one another. I don't think we're totally kind of reached the point where these are going to flatline yet, but you can see they already are kind of slowly going down. So the hope is that that blue bar on the top would stay in the green zone. And we do expect the red one to kind of end up in that yellow zone. And if so, which we have so far, it looks like it's tracking that way. This is a pretty useful finding to kind of validate some of these techniques that I've been telling you guys about. And this right here, what I'm showing you, the green and I took the green scale out of the top because it made the colors look weird and it was hard to track. The green data at the top and the red data, those are the two sections I just showed you. And they're kind of juxtaposed against two other mixed sections that these works are kind of connected a little bit, showing you what we're trying to do is those orange and those blue data, those are really what kind of gave birth to this idea of we need to be able to do this because they all start about the same. If you look at the zero cycles, zero easels, all of these started with really high friction, and yet we ended up in some pretty low friction numbers from some aggregates that we thought were good. So we need to not just look at early friction, but late friction is critical. And I'm going to hand it over to Phil now to take us home.
Hello, folks, and glad to join you. I am coming in as a literal backseat driver today. I attempted to put a video in this and made the presentation a little bigger. I don't know how well this will show, but I wanted to bring in a little bit of the lab piece of this, along with talk about what we're doing in Kentucky. And as I'm gonna have you click on that just in case the video it could be hurting our.
Let me pause it.
Yeah, if you'd pause it there.
Okay.
I just got to thinking the video may hurt audio quality since we're remote. So in the laboratory, you have to start off with some type of machine to make a slab. Not the easiest thing in the world because we're used to making them in round samples. However, if I want to do some of the gyratory, I'd refer you up to what Indiana has looked at, and where they take a series of gyratory samples and they'll cut them and butt them together. I was afraid to start there. I sort of wanted to start with the way the INCAT's done it and the way I've traditionally seen it done, and look more at just the slab. Once you make the slab, of course, on the left, you begin with the polishing device, and you see the water there squirting on the sample. A lot of details, of course, goes into this. You're constantly looking at your tire pressure. Nathan and I were discussing earlier that we even buy the same brand tire. There's so many things that are not standardized on this that we're going to begin working with folks to standardize. And as that's done, this can be more transferable to other locations. Once you have the slab polished, of course, at different phases, you can use the DFT as you see there on the right. And I actually flipped it up because I don't know a lot of people that flip it up. And I'm always curious in how it works. And I flipped it up on the side, and I'm cautious in doing that because there's a little pin in it. You got to make sure it's in the right spot. So you don't want to torque your spring, and the spring is what keeps the thing calibrated. But you see there on the bottom in the right picture, there are, and Buzz showed me a cool tool. I'm going to try this, Buzz. Is this?
Yeah, that's it.
If you look at the rubber pads, those are the little guys that's sitting right there and right there. And when that plate drops, the plate will drop onto the pavement after it spins up, and then it begins to slow down as you hit the brakes. And that's how we're measuring the friction. The sample that you see there in the middle, or the picture in the middle, is simply the device where you take it out to a roadway where you can check it there. So that's the beauty of this dynamic friction tester, is you can measure in the laboratory, and then you can turn around and go to the field and use, whether you're using a locked trailer as you saw, or the scrim with the slanted tire, you can begin to compare this type of data that you have here with the DFT directly to the field. Some things that I wanted to speak on and what we've done in Kentucky that I think would be useful today is while Kentucky has not been looking at, um, while Kentucky's not been looking directly at the higher friction or the ultra high friction, Kentucky, the state of Kentucky is working currently, doing some work jointly with that Federal Highways is looking at, and they're doing that with NCAT. Now, I'm not involved in that, not inferring that I'm involved in that, but that's a contract between Kentucky and, of course, NCAT. Very interesting work, and a lot of folks, a lot of eyes are on that to understand what comes out of it. Where I come in is I'm on the contractor side, looking at this with contractors, because contractors know this type of evaluation will be geared up in the near future. So contractors want to get ready, and how do they understand that? Well, why are they looking at it like that? Currently in states that are having friction problems, such as Kentucky, and I'll just speak on the one that I know of. We have limestone, we have dolomitic limestone, and the limestone's all sedimentary material, which polishes quickly. Now, that's never been a problem until later years when we have fined up our mixes a bit more, affecting the macro texture. Other things we've done is we've added wrap. Now, wrap's not bad, but if you add a significant amount of wrap and you don't know what's in your wrap, it can become a problem, especially on friction. So there's other sources in Kentucky that's running out. And what do you do when you run out of polished aggregate? Well, Buzz and Nathan, these contractors are sitting there having to wait 8 and 10 years. And why do they do that? Well, they have to put it on a roadway that's not traveled too much, and you wait for it to get polished, and then the state will look at it and they'll say, hey, we think we've got a good source now. It just takes it's a long process because we just don't have good tools in the lab. So we see this device, the DFT, as a way to really speed that up, allow the contractor to screen potential sources for friction value. We've never had an option like this before. Looking at unique material combinations. Some contractors may be looking at importing something, not a lot, but let's import 10% of a high friction aggregate, maybe some boiler slag coming out of Ohio, maybe bringing something up from Tennessee from where we are. But again, it can't become our primary aggregate, or the roadways will get where it's just not cost effective for asphalt in pulling off the friction that we need. Maybe look at unique material combinations. I'm sure people are going to figure out synthetic options for this. We need to understand that the friction number 2 is not just a pass fail, but it does degrade over time. And how does it degrade over time? Maybe you need a certain amount for a lightly traveled interstate, but you need a higher amount for a higher traveled interstate. So these tools that we're using today give us options like this that we've never had before. One I would like to add on that I didn't mention here is most recently there was a pavement that went down in the area, and I was asked to go out and look at it. And the reason is there was a concern that could this pavement, where it maybe have had too much asphalt in it, could it cause a problem with friction that could be dangerous to the driving public? It was out of spec, and the agency that would ask me to come out and look at this when they weren't sure of the actual friction on it because they hadn't measured it. Instead of the contractor taking it up, the contractor said, time out just for a moment. If we have these tools, why don't we look at it? And what we're doing here is we're comparing lane to lane. We had one lane that was good, that was in spec. The other lane that was is out of spec, or so it was thought. We compared lane to lane, went back over a period of 6 months, compared again lane to lane, and they're going to look at it again. But as of this time, there's no differences in the lane. So what does that tell us? Well, after a 6 month period of time, does it mean everything's safe? No, I'm not going to say that because I can't say that. What I can say is there's no difference between the lanes. I measured a 0.44 in one lane and a 0.43 in the other lane. And matter of fact, the one that was better was the lane in question. So, and there's no difference in those numbers. So it gives us a tool that instead of we pull the instant trigger of remove and replace, it helps us to evaluate what we have before we go to pull it off. So again, most of my talk and what I want to talk about, Buzz and Nathan, is really on the tools that we have today and how we can take those to the field. We can work with the contractors, screen these potential sources, and hopefully begin to not only do that, but adopt some aggregates that we have not been able to look at, and not only save the contractor money, but deliver a higher quality product on our roads that will save lives in the long run.
All right. Well, thanks, Phil. Thanks, Nathan. I'm going to try to pull all this together and give y'all some implementation takeaways and give you what I think is a really practical example of how this can be implemented. So in kind of the era of balanced mix design and the evolution of balanced mix design, we've got new tests that are available. They vary by jurisdiction. The states are looking at different things, but we have some really useful tools that we think for evaluating mixes for cracking and rutting potential. So we have the tools that we need to extend pavement life, to provide, essentially performance mix designs, but we have to maintain safety. Safety is an essential part of long-term pavement performance. So in other words, it doesn't do any good to build a road to last 20 years if it's not going to be safe after year 5. So this work is essential to that type of thing. So we, as Nathan and Phil both said, we have the 3-wheel polisher and we have the dynamic friction tester that we can use as tools to look out into the future to see what these mixes look like. And we can design to either satisfy enhanced friction requirements or to hit minimum friction values. Like Phil mentioned, if you're looking at approving sources for use for surface mixes, then you might just be looking at minimum friction values, or you could be doing the work that Nathan focused on in his part of the presentation, where he's blending materials to hit higher values. But the point to all this is that this is what gets me really excited about it, because the first third of my career was with Alabama DOT, and I was in the private sector for a few years, and now the last 2/3 have been with NCAT. And I get really excited about the ability to innovate. So these types of performance specifications, they really allow innovation by the private sector. And that's what we really need to do, is to determine the most economical blend of materials that satisfy all of our mixed performance requirements. So that could be as simple as cracking and durability, rutting, and friction performance. If it's an installation where friction is a critical thing. As Nathan alluded to in his presentation, friction designs can take a lot of time and effort. This has been a big learning curve for him, but one of our big goals in this research is to develop estimation tools so that you can essentially have a different page in your mix design spreadsheet that looks at kind of basic source properties, looks at the sizes of the stockpiles, looks at the macro texture that you create when you blend those materials together in your design, and estimates friction. And then that can be backed up with the testing that we do in the lab with the 3-wheel polishing device and the DFT, all correlated to performance that we've proven on the test track with accelerated performance testing. So we're really excited about this, and we actually have some collaboration planned between NCAT and Rutgers and Phil's Bat Lab and others. We want to work on standardizing this process. We got a lot of experience with this now, and we really want to pull the people together that are working in this field and come up with a way to say, okay, this is the framework, this is how this type of work needs to be done, so that we can kind of unleash the innovation that we really need in the industry. Now, I want to end by giving you a really practical example of how this can work. At the NCAT pavement test track, we did a mix design in 2018, and this was research that was funded by the Alabama Department of Transportation, and they wanted us to develop a high performance preservation thin lay. So what we came up with for that mix was a 4.75 in-mass SMA, and kind of, I guess I should put air quotes on the SMA because it doesn't have any stone in it. It's a screenings mix, sand and screenings mix essentially. But so we came up with this 4.75 SMA mix. It did extremely well on the track. We've continued traffic on it in this cycle, so it's way over 12 million equivalent single axle loadings now, and it's a 3/4 inch preservation thin lay. So it's an outstanding mix. industry, the aggregate industry had to respond to the demand that has created, because Alabama now has implemented this mix. So they're manufacturing nines, a really uniformly graded aggregate. So a really simple example of how we can implement enhanced friction mix designs is, say you're a contractor and you're paving a road and you get to an area where you've got a little intersection with maybe an awkward approach angle, and the agency says, well, we need enhanced friction over this 300, 400, 500 foot section of roadway. Well, when you've got that 475 SMA design, all you do is dump calcined bauxite in the bin that you're feeding those nines from, and you swap over to that material just for the length of road that you need. And then as soon as you get back out of that, you get back into the conventional crushed stone nines that are part of the mix design. That's a really easy way to implement this type of thing, and that's going to give you, again, at the half-life of the HFST, that's going to give you the same friction performance. So you're going to get really good friction initially from a mix like that 475 SMA that's got calcined bauxite in it. But then, after you get a little bit of wear and you expose more of that material, it's going to be equivalent to the HFST. So we're really excited about that, because it's pretty easy to implement, especially when you combine it with the tools that we've talked about in this presentation.
Buzz, I had a comment on that. So Kentucky, it's funny. It's like, why are we having these friction problems now in Kentucky when this rock, we haven't changed it in years? And contractors wanting baselines, and we don't have the calcite and the bauxite and the granite. God didn't bless us with those where we're at. We have to go down 400 feet and get the limestone. Well, if you look at what we used to have more open mixes. And so one of the conversations I had with the contractors, maybe, we may not be able to change the aggregates, but we can sure look at going away from the 3/8 mix, but go to a half, and work with the contractors on that and develop and make these limestones work by using the best micro texture we can get, but we're limited. So now let's improve the macro texture with that combination. Now we're going to end up with something that's going to work for us in that state.
And that's the kind of innovation that this lab process that Nathan talked about, and that Phil has the equipment to use for studying in his laboratory. That's the kind of innovation that we need. Let's establish our target values on a conventional roadway. What is a safe minimum, and let's use the most economical combination of materials to hit that safe minimum.
That's right.
And then when you need enhanced friction, we use the same tools with some imported material to hit enhanced friction in areas where we need to. So there's our email addresses. We got a few minutes left here, and I think Nathan is queued up so he can look at questions. If we have any questions, Travis, are you still online, or did you have to board your plane? We're all traveling right now, and but we're really excited about these implementation webinars, so we're supporting it.
I am actually just on the plane just now, Buzz. But Nathan, if you could read those, I think there's been some good questions in there. I particularly like the one about, if we're going to use more calcite bauxite, do we think maybe the price will come down? So I think that's a great one to read as well.
Yeah. So there's a few other these. We'll try to answer some of these quickly. Is the loss of friction due to the loss of bauxite aggregate from the epoxy, abrasion, and wear of the bauxite, or both?
It's just the wear process of the bauxite. So the bauxite is not rounding off and wearing out. I mean, it really is. I guess adhesion is a good word to describe it. Over time, even with perfect quality control and perfect materials, you see it over and over again on the test track, regardless of what material you use, what kind of chips you use. When you're using epoxy, eventually you have kind of an adhesion failure because of environmental exposure and traffic. So it's not like a delamination, like if you put epoxy bauxite on top of a pavement that's got a moisture problem. That's not what this is. This is just particles that are gradually coming off over time.
So Dave again's got a couple good questions. We'll start with the first one. What is the general availability of calcined bauxite? Is it practical to use this material in anything other than in high priority locations or is it possible that more widespread use will make calcined bauxite more readily available at a reasonable price?
I'll jump in and answer this one, and Nathan, you might want to follow up, but we have the perception that calcined bauxite, oh, you got to ship it from another country and barge it, and it's just super expensive. And that's not necessarily true, because there are states, Alabama is one of those states where bauxite is mined and run through a kiln actually in Eufaula, Alabama. So and that's kind of in South Alabama for those of y'all who are not familiar with the geography of Alabama. But so that's a material that actually could be shipped pretty easily to Georgia and Florida and Alabama and Mississippi, states like that. Arkansas is another source of bauxite. And one of the things I like about this process is if you're going to build an HFST epoxy calcined bauxite surface, then there are really, really strict chemical requirements that you have to hit for that bauxite that drive the cost up. Well, through this laboratory process, we can look at the long-term performance of these enhanced friction asphalt surfaces that we're talking about, and you can potentially use the bauxite that kind of has a relaxed chemistry and let performance drive the use of those products. That takes a chunk out of the cost of the bauxite when you can relax the chemical requirements of it. So I think the answer to the question is the tools that we have in the lab now give us the ability to use bauxite in a more cost-effective way. You don't want to pay 5 miles with it, as in the example that I gave. You want to pave a road with conventional materials, and then when you get into specific areas where you need the bauxite, then you swap over to it, do hot swaps during production, and then you swap back into conventional mix thereafter.
And calcined bauxite is not the only thing that is expensive in high friction surface treatments. The epoxy itself is expensive, and just the application process is relatively expensive as well. So if we can get the benefits of calcined bauxite as a friction aggregate, but insert it in as an aggregate into asphalt pavements, we kind of get the best of both worlds there in some cases.
I did some rough calculations, and I want to say the cost savings between a thin lay where you're burying, calcined bauxite in 3/4 inches of mix depth that gradually wears to exposure over time. I think it was something like 20% cheaper. You could build that pavement maybe 20% cheaper than you could place epoxy calcined bauxite, because I think the cost of the epoxy can be as much as $15 a square yard. I mean, it's extremely expensive.
We got 2 more. Let's try to knock these out.
Okay.
All right. So Dave had another question, and I'll let you start, and I can jump in. And Phil, you're welcome to as well. How does steel slag compare to calcined bauxite with respect to hardness and/or polishing over time? And what other common optional aggregate replacements are there in the marketplace?
Well, you've been looking at that for some of our other research, so why don't you answer that?
Yeah, so we're actually gearing up we're about to start laboratory testing and some work for another DOT, really looking at that question, Dave. From literature, slag, it usually does provide a very, very good quality friction aggregate. I can't think off the top of my head of any studies that compared them head to head, specifically calcined bauxite in an asphalt mix and steel slag in an asphalt mix. I may just be drawing a blank. I would imagine that steel slag provides less friction than calcined bauxite, but that's because so does everything else. But it doesn't mean that you necessarily shouldn't use it. The steel slag is in general, now not all slags are the same, but in general, steel slag does provide a very good friction aggregate. And again, it's because as Buzz mentioned earlier, with using calcined bauxite in an asphalt mix, as you begin to wear it, well, what are you exposing? You're just exposing more calcined bauxite. As you polish and abrade steel slag, it chips and it breaks in different ways that it creates really jagged and rough texture, which directly affects the microtexture. In relation, to some of the other questions about what are other common optional aggregate replacements on the marketplace, we've seen stuff with sandstone, for example. There's some sandstone sources, and Oklahoma's got some really good ones when we've done some work on the test track looking at sandstone sources. There's lots of stuff like that. Granite,
Trap rock,
up in like the Northeast, trap rock's a really good source. Taconite is another that's a kind of it's not a typical aggregate. But it's kind of up in the north where we've done some work using taconite as well as a friction aggregate.
But the point is we've got the laboratory methodology. We have the tools now to evaluate different combinations, different sources of materials, and that frees us up to innovate into the most economical solution. So we're really excited about that.
You know what's interesting too, Buzz, is I know you all seen this, is that when you look at cracking, the granites tend to do the best, then maybe into your quartz and then into your limestones when you look at anti-cracking or crack resistance. And it seems that friction may follow that same thing, to where, again, high quality aggregate is high quality aggregate. And you know, this is going to be a interesting play on the economics when a contractor begins to put all these factors together, and you look at rutting, cracking, and some states now friction.
That's right.
Yeah. So I'm answering there's a couple questions here that were answered just via the chat. So I encourage you guys to look through that.
Travis, are you still with us?
I sure am. I want to make sure and thank you all, Phil, Buzz, and Nathan. Thank you for taking time out of what is a very busy day for you to go ahead and do this implementation webinar. I think there's been some fantastic information shared. I really like how we started with the ground there, Nathan, and talked about the micro and natural texture to help folks out that may be new to this. And then we're able to go deep as well with some of the things that Phil, that you brought on as well there. So I do want to remind.
Can I make one more statement before you close us out, Travis?
You bet.
Really, when we talk about microtexture and macrotexture, really you're kind of looking at think about roughness or wavelength of surface irregularities. And the way I kind of simplify this is I say microtexture comes from the quarry, macrotexture comes from the asphalt plant, and then roughness on new construction comes from the paving contractor, from the asphalt paving. All of that stuff is just looking at surface irregularities at different wavelengths. So
Yes.
that's don't be scared by this, don't be kind of distracted by, well, what's the difference between microtexture and macrotexture? It's actually quite simple. So I'll hand it off to you now to close us out, Travis.
Okay. No problem. I want to remind everybody and invite them to go ahead and jump on and join us again on August 18th. And we're going to talk about using pavement curves, pavement deterioration curves and preservation to keep our systems going. We'll have Buzz and Dr. Ed Granavargas, and probably we're going to have a guest speaker as well then. So given that, thank you again, everybody, for joining our implementation webinar series, and we look forward to seeing you next month. Thank you.
Have a blessed day, everybody.
Thanks.